minus P times Vf minus Pi for constant temperature. W would be this. We will need to substitute for volume dependence of pressure so that volume could be so that this could be integrated. And for this, if you use the Boyle's law, I did this last time. If you have it in your notes, this comes out as I will quickly show you. W will be equal to minus nRT times log of Vf over Vi. We don't need to do anything because this is the expression. If pressure is constant, pressure is out of the integral sign, and whatever change in temperature, it would be there. Yes, and therefore that parameter will come into play in things like this. Okay? So his question was, why isn't there any temperature dependence over here, for example, constant pressure? And I said that temperature dependence isn't there because there is this pressure is constant, and in this expression, simply volume change is what shows up. And over here, in this case, temperature is constant, is being taken out as constant, and an expression, we write this expression. Over here, note that if I were to plot log of x as a function of x being anything, the log varies in this manner. This is the way log goes, where log of x is equal to 0 and x equal to 1. Everybody remembers that. And that at x equal to 0, log of x is minus infinity. And therefore, log of x changes sign at x equal to 1, which means over here, you can clearly see that if final volume is larger than initial volume, which means an expansion, then this quantity is positive and therefore work is negative, consistent with our convention that we described yesterday. And vice versa, if final volume is smaller than the initial volume, then this is less than 1. When this is less than 1, then log is negative. Log is negative, therefore W is positive. Work is positive. So compression is W positive, expansion W negative. Reinforces what we described yesterday as our convention for putting sign with W. And then the fourth thing I was about to do and left, when the time was up, was when work in adiabatic condition. Adiabatic condition is the condition in which system is completely isolated. No heat flows in, no heat flows out. Okay? Insulation. No heat flow. We will see today later that under that condition, P v to the power gamma comes out to be constant. P v to the power gamma equal to constant is replacing the law of P v to the power. Boyle's law was P1 V1 is equal to P2 V2, or P1 PV is equal to constant. Was Boyle's law. For constant temperature, at constant temperature, P times V is constant. This was Boyle's law. We used that to derive this expression. This was done in the last lecture. In this one, we therefore in the adiabatic conditions, PV to the power gamma is constant, and gamma, I wrote quickly yesterday that gamma is ratio of heat capacities, and we will talk of heat capacities today. Okay, his question is, under adiabatic condition, no heat goes in and comes out. So wouldn't that be equal to saying that the system temperature remains constant?
No.
And we will see today also, hopefully by towards the end of the lecture, that there is something called adiabatic expansion, where you keep the system completely closed and expand it. That causes cooling of the system. Adiabatic cooling is a very important phenomenon which is used for cooling the system. So your question is answered. That temperature doesn't remain constant. Okay? In this particular case, we will, I've just, if we say that P v to the power gamma is equal to constant, it amounts to saying that I could take one point where P1 V1 to the power gamma is constant, and I can also take P2 V2 to the power gamma, the same as P1 V1 to the power gamma. I can write that law in this particular manner. And therefore, I can say that P times V is, this chart is horrible. Either the chart is horrible or something has gone wrong with the board. The board is certainly today very slippery. P times V to the power gamma, P times V to the power gamma is equal to P1 times V1 to the power gamma. And you can choose 0.1 to our convenience. Yeah. Or not for all gases, no. And yeah, for under different conditions of pressure and volume, yes. Okay? Because it is a ratio of heat capacities, and heat capacities are characteristics of the substance. So as long as you're using the same substance, this ratio gamma will remain constant. So his question was, would gamma remain the same under all conditions? And we just described that. Okay. If this is the case, then I can write P as equal to P1 V1 to the power gamma over V to the power gamma. Okay? And substitute in that expression top. W is equal to minus integral, and I will have V1 Vi Vf P, I will replace with this, and here for P1 V1 I will take pi vi. I can choose any point, right? I can choose pi vi to the power gamma. Over now, this v is the one on which we are integrating. So this is v to the power gamma times dv. So this is a fixed thing, is not a variable. You have to take it out and perform the integration. So W is equal to minus pi vi to the power gamma times integral dv over v to the power gamma from vi to vf, initial volume to final volume. Correct? And here I am reminded that if I have an integral, we call ourselves dx over x to the power n, that this integral is equal to 1 over, there will be this n factor coming out, minus, minus 1 to the power n minus 1 times x to the power minus n plus 1, and x to the power minus n plus 1 actually amounts to saying 1 over x to the power n minus 1. So this is what it should be. Okay, I should write it this way: 1 over x to the power n minus 1. This is the value of the integral. So we substitute this over there, and then I am going to leave the rest of algebra for you. I have done the essential bit. Final answer is that W is equal to 1 over gamma minus 1 times PF VF minus PI. Okay? In going from here to here, you should not face any difficulty given the value of the integral. Okay. So we have defined therefore 4 different ways in which work can be performed, and we have seen 4 different expressions for work in each case. And today we will, in our agenda, is to also prove this expression for adiabatic conditions, and also to look at the heat flow. The next point is to look at heat flow. Remember, work, before I start this, work depends upon path. Therefore, it is not a state variable. You cannot say that the system is in this state and therefore it has so much amount of work in it. No, you cannot. Work is only when energy is transferred into work. Heat, Q, is also path dependent. Depends on how you supply heat to the system, and therefore Q is also not a state variable. We talked about it in one of our initial lectures, perhaps last week, in the first lecture perhaps, when we said that heat is not something that resides in the system as heat. Heat is heat when actually energy flows. That energy which is flowing is called heat. All right. Now, as in the case of work, we defined, I'm taking a few checks now. As in this case of work, we defined that when W is negative, it is work done by the system. Okay, expansion, as I just explained over there, it is expansion. And W positive is work done on the system. After the last lecture, the students came and tried to understand this and argued that whatever you are saying about this is true for work done by the system in the expansion and contraction. The contraction could also be work done by the system. So why isn't that positive? But I said it's a matter of convention. We decide on a convention that for one process we will call W negative, for the other we will call W positive. Okay? Similarly for Q. Q positive for heat entering the system and Q negative for heat leaving the system. Okay, system or substance or whatever. Okay, again taken to as a convention. Now, when W is positive and work is done by the negative. When W is positive and work is done on the system, this increase. Oh, I have not yet introduced internal energy. So let me not make this statement yet. I will come back to it after a while. The interesting thing is that neither W nor Q are state functions, which amounts to saying that if you were to take dW over a closed path, this will not be equal to 0. This statement is the same as this statement. Okay? If you have a state variable, then that state variable, if you take a long route and then come back to that same state, the value of this is that state will be the same. But those which depend upon paths, this is not the case. When you come back, you will find the value of W to be different, or value of W in the sense that W, some amount of work would have been done. Similarly, this particular statement amounts to saying that dQ is not equal to 0. So these two statements basically are contained in these two, if you want to call them equations or inequalities, that they are not equal to, they don't vanish. However, experiments tell that if you were to take W and Q, dQ, take a sum of them, and then that actually does vanish when you take a loop, go on a closed path, come back to the same point. It has the same value. This is an experimental observation, an empirical result, because of which you therefore immediately you can argue that something over here must be a state function. All state functions have to have this property. Something over here must be a state function, and you call it u, and you call it actually du, and you say there is something, u therefore is a state function. Okay? And give it the meaning of u as internal energy. So you therefore have a situation where you have a state function now defined from some experimental observations, and that state function happens to be internal energy, and you will have plenty of time to explain what this internal energy is. This du equal to dw plus dq happens to be the first law of thermodynamics. And first law of thermodynamics actually is a statement in the law of conservation of energy. It says that energy has to be conserved. It is also something, energy has to be conserved, energy system, even if the first law is also said to be a statement that forbids perpetual motion of the first kind. This has been a dream of mankind for a long, long time, to make machines which will work for us. So you sit back. I'm coming to it. Or there is this of a second kind also. Therefore, it is a first kind. Okay. The dream has been that machines will work for us, and we will sit and relax, enjoy life. And the perpetual machine of the first kind said that there will be a machine which will work all the time. I don't know, we don't care where it will get energy from, it will continue to work and will produce a work for us. So there will be this machine which will continuously produce work. This law said, no, you can't do that. Energy has to be conserved. If you use some energy, and if you work in energy, if you produce a work, that will have to come from some input of energy. And that input of energy has to come from somewhere. There has to be a conservation of energy. Okay? Conservation of energy is given by this expression also. So this is a law which, in fact, and there is of course the second law which says that you cannot continuously take all the heat that you have and convert it all into work. That in fact what you have is that you have perpetual motion of the second kind, which is that you, whatever energy you have, convert it all into work, and then reconvert it into heat and put it back into work, and so on. So you have a machine which works perpetually. Works, and then that work produces heat, and you put the heat back, and the system will continuously work. And the second law of thermodynamics said you can't do that. Second law of thermodynamics said you cannot convert all the energy you have into work. There will be losses. Okay? And actually, people continue to think of inventing machines which have either efficiency 1 or greater than 1. And I remember some people from when I was at Nayyar University, some people visiting us from a military lab, defense lab, and saying that, look, we have made a machine and it doesn't work. Tell us why it is not working. So they said that, look, what we have is that we have a tank of water filled with water, and we let out water from below, and when water comes out, we put up a turbine. It turns the turbine, and then the water falls into this turf below, and then we say that, okay, there is this loop through which this water is taken back into this. So they say that, look, there will be this vacuum created up there. Vacuum will be created as the water falls. The water will fall over here. Vacuum will be created, and because the vacuum will be created, therefore this water will be sucked back, and therefore you will have a perpetual machine. So they came to us. They were very puzzled that their machine was not working, and they came to one of our colleagues at Nayyar University and asked, why is it not working? And he said, have you read the second law of thermodynamics? So he said, what has thermodynamics got to do with it? There's no temperature involved. There's no heat involved. What has thermodynamics got to do with it? And then they had to be told that, look, thermodynamics and laws of thermodynamics don't mean only heat and temperatures. They basically talk of things in a more universal way. So I thought that, there was this, and of course those people went away disappointed. They thought they had made a huge discovery and they had come up with a bright idea. I thought they were, perhaps, in our society we have a large number of crackpots, so they may be one of some of those. But it turned out that actually this world is not short in crackpots. So if you want to really enjoy the work of those people who continue to invent machines of this nature, visit internet and Wikipedia, for example, and you will find a number of examples, very, very recent examples where people have taken out patents on machines which will violate basic laws of thermodynamics. Okay? Simply because they have not read, studied thermodynamics. They have not read laws of thermodynamics. Okay? So you will not make these mistakes because you know laws of thermodynamics. Okay. A couple of good, interesting points that come out of it. If you were to calculate internal energy of an ideal gas, then what is it called? Molecular theory of gases? molecular theory of gases क्या कहते हैं नाम देता है? Kinetic theory of gases. Kinetic theory of gases gives us a very good idea of what it should be. Ideal gas means no interparticle interaction. So whatever energy the system has would be simply kinetic energy of particles. Therefore, only kinetic energy. And internal energy of the system would simply be the sum total of the kinetic energy of all the particles. And you will recall that if there are n particles in the system, then kinetic energy of n particles is n times half m v square average. Right? This would be the kinetic energy, or this will be the internal energy of the system. And also, we have seen this earlier, that this will be equal to 3 by 2 times K times temperature. We have seen this already. Which means that internal energy is given entirely by temperature. Or for an ideal gas which has no interparticle interactions, temperature is a measure of the internal energy of the system. Number 1 point. Number 2, let's also define the quantity that I wrote over here and I haven't defined yet, heat capacity. Heat capacity is defined as, rise in supplying heat. Raises the temperature of the system. Okay? This is understandable, right? Supplying heat to the system would raise temperature of the system, which means that you can, which means that dQ will be proportional to dt. The larger the amount of heat you supply to the system, the larger will be the increase in temperature. That is understandable, right? So this will be this, and therefore I could write dQ as equal to C times dt, where I will call C as heat capacity. How much of heat you can take for a given rise in temperature? So C is dQ by dt. Amount of heat the system would need to increase its temperature by a certain amount. By the way, this is actually this is a response function of the system. Whenever we want to know about some system, what we do, we act on the system and then look at the way system responds to that action. So if you want to see this color, we shine light on it, and the system reflects color of a particular kind, and we see the color. We want to measure electrical conductivity, then we will pass current through the system and measure the amount of current that passes through the system, and that will be very characteristic of the system. So system responds to an external stimulus in its own way. Every system would respond to an external stimulus its own way, and that therefore is how that response that will be the response function, and response function will be peculiar to a system. And will describe the characteristic of the system. So heat capacity, therefore, is a characteristic of the system. It is something which you can you measure and then you tabulate, and you say that at this temperature heat capacity is this, at this pressure heat capacity is this, and so on. Now this heat capacity is because of Q path dependent. And path dependent in the sense that it will be different when you measure it by keeping volume constant or by measuring it by keeping pressure constant. So you have therefore Cp and Cv, heat capacity at constant volume and constant pressure. And it is these two things that I wrote over here, and gamma is a ratio of these two things. Okay, and the specific heat capacity is what you call normally specific heat. Is per unit mass of the system. So normally it is written in lowercase and uppercase, and over here writing on a blackboard lowercase and uppercase differentiation is different, but CV will be CV divided by M divided by the mass of the system. Per unit mass, you find it out per unit mass of the system. Okay? Now, if you were to calculate heat capacity at constant volume, constant volume means no work. Oh, right, as we have been saying over there too. No work means du, dq, du is equal to dq. All right. By the way, I think I did mention it in the very first lecture that these dWs and dW and dQ normally people write with a slash on d to show that these are not perfect differentials. That these to express this particular property, it is written as this and this, and therefore they sort of are particular about it. As I said in my first lecture, I wouldn't be very particular about that thing, so I am not using that slash because it will be understood that this is something which depends upon path and not to be taken as a state variable. Now dq is this, and therefore if you write CV, it is dq by dt at constant volume. It will be equal to du by dt at constant volume, right? And du we just saw is for ideal gas. U is 3 by 2 kT. That is. And therefore, CV is equal to 3 by 2 K. For an ideal gas, its capacity is 3 by 2 K, which, if you recall, NK is equal to NR. So you can also express this in terms of R, and molar capacity can also be expressed in. The units of CD are joules by definition, but to degree Kelvin. Okay. कुछ लोग लिखते हैं, कुछ मुझे से पुराने लोग अभी भी लिखते हैं, लेकिन नए लोग नहीं लिखते, तो ओके, ऑलराइट। देखें जरा, अच्छा नंबर लेने की कोशिश। I will derive a very, as I said, I will derive a very important relation now. I will derive a very important relationship between Cp and Cv for an ideal gas. If you were to take here volume and here pressure, and you take two isotherms. Isotherm is, as I said, is something like this, and there is another isotherm. This is at temperature T1 and this is at temperature T2, and T2 is greater than T1. This is often the case. And now, because U depends upon temperature only, because U is equal to 3 by 2 kT, depends upon temperature only. So if I go from this curve to this curve, from whichever point of this, I go to whichever point of this, the value of U will be the same. Okay? I go from here to here, or here to here, or here to here, and here to here, wherever I go. The value of U, change in U, will be just the same, because change in U is equal to change in temperature. And these are isotherms. Each point on each of these curves is at the same temperature. Isotherm. I'm sorry? Sure. I said that change in U will be the same. So let me make this statement clear. Same du for the same dt. You will agree with this, right? And as you go, from whichever point you go to any other point on the other curve, you have the same difference in temperature, and so therefore the amount of the change in internal energy will be exactly the same. Now, choose two parts. I now have to look at the drawing that I have. Yeah, okay. Suppose you go from here to here. This is point A and point B. or I could write point A B over here, point A here and point B here, and you go from here to here, this is point C. Okay? AB is supposed to be parallel to B. If it is not, then that is you will by for drawing. Okay. So A to B and A to C are two different. If you were to look at du in the case of going from A to C, temperature changes, and therefore this is equal to N times Cv times dt. dt is T2 minus T1. And this is my way of saying that this is the molar heat capacity, because I have multiplied it with the mole number N. Okay? This is molar heat capacity, as I said, because I am multiplying with mole number. Okay? If I multiply heat capacity with mole number, then this will be total heat capacity. Molar heat capacity multiplied by mole number. And in this particular case, I'm sorry, I made a mistake. A to C, yes. A to C is the case in which why did I say this? Let me explain. A to C is constant volume. Right. A to C is constant volume. And internal energy, therefore, change in internal energy is the same as change in heat capacity. And change in heat capacity happens to be Cv times dt. Right? And therefore, I wrote here N times Cv times dt. Does it make it clear? And if, on the other hand, I take du when going from A to B, I don't have the luxury of constant volume and therefore no work. It is both work as well as change in heat. And that is equal to dq plus dw. And dq is now, you see, this is dq is this time because pressure is constant. If you go along this line, pressure is kept constant. So you will have Cp times dt. This is dq only. And dw is work, which is pressure times volume minus pressure times dV. I hope I am not writing too small. People at the back, can you see? Can you see? Okay.
Yeah.
Fine. Now, for an ideal gas, PdV minus PdV is equal to N times R times dt, right? Because the equation is PV is equal to N times R times P. And if you are saying that pressure is kept constant, volume changes, temperature changes. So volume changes, temperature changes. Everything else given by this equation. Are you guys in my writing on that board? Is it okay? You can see it, right? And I can substitute that over here and I can substitute things over here. So the du in the case of A to B happens to be n times Cp. Now this is my way of saying this is molar heat capacity. I've written in lowercase c multiplied by mole number n times dt, and then minus n times r times dt. So, what is the conclusion of all of this? I started off by saying whichever way you go, the change in internal energy is going to be the same, which means these two expressions should be the same. Therefore, n times, I used it already? Therefore, n times Cv times dt is equal to n times Cp times dt minus n times r times dt, and therefore it shows that Cv minus Cp is okay. Let me write it in a proper form. Cp minus Cv is equal to R. Okay? Comes out straight away from this equation. dt cancels out everywhere, n cancels out everywhere, Cv is equal to Cp minus R, which is saying the same thing as this. So heat capacities, the difference of two heat capacities is equal to R, is a relation valid for ideal gases. Sorry? This is these are okay. You caught me there. These are small c's. Okay? Molar heat capacity. If I had done total heat capacities, I would put a molar number n over here. Okay. If you are looking at ideal gas, again, in ideal gas, Cv is equal to 3 by 2R, and this immediately gives you Cp is equal to 5 by 2R. And therefore, gamma equal to Cp over Cv equal to 1.67. Usually, for most of the substances, it is around this number 1.67. 1.8, 1.4, 1.3, 1.9, it could be one of those numbers. So this is generally the range for difference between ratio of heat capacities. The other thing that I intend to show today is the law that I have used already, that for in adiabatic conditions, PV to the power gamma is equal to constant. I thought I would show it over here. First I will show it over here, and then I will show a very important consequence of that fact. Showing P times V to the power gamma equal to constant. Right? See, we make use of the expression Pu equal to n times Cv times dt, which we have already used, and say that under adiabatic conditions, dq is 0. All right. In a diabatic condition, dq is 0. There is no heat flowing in or flowing out. System is completely insulated from outside, from the surroundings. And therefore, your expression du is equal to dw plus dq, and dq is equal to 0. So, du is equal to dw. And dw happens to be minus p times dv. And so you have therefore minus p times dv equal to minus n. Okay. This is du is equal to okay. So minus this is equal to du, which is equal to n times cv times dt. I have only used this, rewritten this equation over here, with dw on the left hand side and du on the right hand side. Also, we note that for an ideal gas, PV is equal to nRT. So we are talking of ideal gas. PV is equal to nRT, which means that if I took a small variation in the quantity called P times E, on the right hand side I will get n times R times dt, because n and R are constant. Okay? And the left hand side is actually P times dV plus V times dV. When you take small variation in the product, you write it in this particular form. So here is an equation in which V is changing and P is changing and T is changing. All three variables are changing. Alright? And here I can use now P times dV. P times dV I have already worked out. So V times dV is equal to nR dt minus P times dV, and so it is equal to nR dt plus n times Cv times. Am I right? What I have done is I have taken VdP and taken this quantity onto the other side with a minus sign, and minus PdV is equal to plus NCV times dt. And the advantage of doing this is that I can write this as equal to N and then R plus CV times dt, and I have already just worked out, I just worked out that R plus CV is equal to Cp. So this is equal to N times Cp times dt. So VdP is equal to this. Correct? And just a couple of more, few more steps, and we will come to the go to the Am I not clear at somewhere? It's okay. How did I conclude this one? Because I said that this is the relation between Cp and Cv. So Cv is equal to Cv, R plus Cv is equal to Cp. Okay? R plus CD. How did I what? Oh, I haven't come to that conclusion yet. No. I'm only changing the board because there's no space. Okay. So, and in adiabatic conditions, we have two equations. P times dV is equal to minus n times Cv times dt, and V times dP equal to n times Cp times dt. Do you agree? We have these two equations over there. Is it okay? So I can take divide one by the other. So V dP over P dV is equal to, I divide this by this, dt cancel out, n cancel out, and minus Cp over Cd, which I called gamma, so minus gamma. Right? Anywhere you find me not explaining enough, feel free to stop me. So I can write things over here. dP over P is equal to minus gamma times dV over V. Okay? And here I can do the integration. And I do the integration from P1 to P2 and V1 to V2. I could write VI to VF and PI to PF, all the same. And from these integrations, I will get log of P2 over P1 is equal to minus gamma times log of V2 over V1 and therefore this is equal to log of, I'm not changing them, making them upside down, V1 over V2 to the power, no, hold on, let me keep, do things step by step, minus this to the power gamma, this is what the log algebra tells us. Sorry? I forgot to write the subscript V2 over V1. Okay? And therefore, and actually minus sign can also go in there. So, log of V2 over V1 to the power minus gamma, which is the same as log of V1 over V2 to the power gamma. Okay? And therefore, because it is log on this side, log on that side, we take exponentials on both the sides, and we will end up by saying that P2 over P1 is equal to V1 to the power gamma over V2 to the power gamma, which is to say the same thing as P1 times V1 to the power gamma is equal to P2 times V2 to the power gamma. All right? Am I too fast? Okay. So this is the law that I started. I started by saying I will prove it. P times V to the power gamma is equal to constant is what I have actually proved over here. So P times V to the power gamma is equal to constant. And I will now spend some time trying to show the consequences of this. In terms of consequences, note that I can write down this expression in a nicer form. PV to the power gamma is equal to constant. I can write as P times V equal to times V to the power gamma minus 1 equal to constant. So the same equation I wrote in this particular form. Okay. V to the power gamma, I divided the V to the power gamma into V times V to the power gamma minus 1 is equal to constant. And therefore, P times V is, you know that P times V is some constant times T. So it is actually saying that T times V to the power gamma minus 1 is equal to constant. What have I done? I have used PV equal to some constant multiplied by T and RT, you know, and an R are both constant. So PV is constant times T, and that constant times T that I wrote, that constant I took it over there and threw it into this constant. So T times V to the power gamma minus 1 is equal to constant, which actually means that I can write V1 Ti Vi to the power gamma minus 1 is equal to Tf Vf to the power gamma minus 1. And consequently, I can write Tf equal to Ti times Ti times Vi to the power gamma minus Vi over Vf to the power gamma minus 1. The important thing is that gamma is greater than 1. So gamma is greater than 1 means that there is power, positive power to Vi over Vi. Okay? And this is significant because it says that if this quantity is larger than that quantity, then Tf is larger than Ti. I'm sorry. Sorry. This is this is a fraction of that quantity. Gamma minus 1 is positive, and okay, I need to say this following thing. If Vi is less than Vf, which is when expansion takes place, then Tf is smaller than Ti. If, on the other hand, Vi is larger than Vf, which is when compression takes place, then Tf is larger than Ti. This is important because it talks of adiabatic cooling and adiabatic heating. It tells you clearly that if you have a gas under adiabatic conditions, then and expand it, completely seal it off from outside, you have a gas that is completely sealed off from outside, you have some styrofoam kind of a material that doesn't let any heat go in and come out. and you put in here a piston, and you push the piston out, increase the volume, then the gas inside will cool down. And if you press it down, compress it, decrease the volume, then the gas will heat up. Okay? This is adiabatic heating and cooling. Often, when things happen too fast, then heat doesn't get enough time to dissipate, then that actually mimics the adiabatic condition. And hence, we see this kind of compression heating up things in, for example, the pumps, the air pumps that we use for putting in air in bicycles. When we push this in and do it pretty fast, then the gas that we compress inside to put into the tire or into the tube heats up because it is compressed, and therefore you can feel the heat on the pump itself. Okay, and if you expand it, then it is cooling down. I can show it in the last minute. In the last minute, I will show you a beautiful expression of this in terms of a PV diagram. If you have an isotherm and an adiabat, the difference between an isotherm and an adiabat is that isotherm is P times V equal to constant. And adiabatic curve is P times V to the power gamma equal to constant. Right. And since gamma is greater than 1, therefore, with respect to volume, this curve is suppressed. And here, if you try and, under adiabatic conditions, if you try and go from, so you have therefore this is another isotherm. You have isotherm and isotherm. Then under adiabatic conditions, if you expand, you actually take it from here to a higher temperature. If you expand, you take it to, no, I'm perhaps not explaining it rightly. T1 and T2, it will take you to, from isotherm, it will take you to cooling effect. It will take you from, okay, the isotherm is taking you, the last bit. The adiabat actually comes like this. It comes like this. And therefore, in adiabatic expansion, when you come from this volume to this volume, you actually cross from higher temperature to lower temperature. And that is what this entire mathematics explains. And I will see you next week. Any other questions?